Okay, so yeah, welcome to today's lecture in deep learning and neural networks. And in this 15th lecture today, we want to start with, I guess, one of the most hyped topics at the moment, foundation models. So we want to see what foundation models are. Then we'll hopefully see that we have all the basic knowledge to understand and build them. So maybe hopefully the first surprising thing for you will be that you know everything, but don't worry. Then we'll cover, based on that, a lot of things which are new to that. So while the network architecture and these things you all know, the application of especially large language models is very interesting because it gives us somehow a new way of how to extract the knowledge that is inside the networks and a quite different way of using them, which is typically referred to as prompting and in-context learning. And then we'll also look at the end at size, because that is one important thing here, and at multimodality. So while we initially start with text-based models, of course, it's very interesting that you want to have models. If you want to have more general knowledge, of course, it shouldn't be purely text-based, but you want to really have it covering a lot of domains. So what are we talking about? So the most common application, I guess you all know by now, ChatGPT was somehow, one of the biggest foundation model and most prominent one. I guess all of you have used it at some time. And here again, the very interesting thing is that, there is not a completely new idea behind it. It's not a completely different architecture or something like that. This is more like standard, but we'll see by scaling things up, we really explore very interesting phenomena so that we can really use this as a very helpful tool. So we can ask questions about general knowledge, and the model is typically able to answer them based on just reading large amounts of data and extracting them and finding them. The basic technology behind it are large language models that we want to see today. And then we'll see on Tuesday, we'll look more into, while this is really surprising and effective, we'll see that one problem is that they sometimes don't really do what we want them to do, but something else. So then we still need some way of later doing some type of fine tuning or instruction tuning, as it's then called, and that we'll cover on Tuesday. What a language model is, hopefully you all know by now. So it's a general task of predicting the next word based on the history. We briefly covered very shortly once when we talked about self-supervised learning that this was done before neural networks with statistical models where we had to use a Markov assumption that we can only take a limited context. The very nice thing is now, since we're using these types of neural networks, we can cover significantly more. And this can be done with neural networks which use sequences. So typically, initially they were like using RNNs, and currently the most common way is to use transformer-based models. There also works on, if you still remember some time ago, a lot of state-space models, especially trying to handle better long-range context. They are also being used. Then the way of applying them, we have discussed that before, we'll cover it again. So it's like that you really just always predict the next word and have everything in the history. The big thing is that people now call it large, and their large refers to two things. On the one hand, large in a way that we have many, many parameters. So when we're looking today at parameters, we're talking about billions of parameters. And the other thing is the data size. Hopefully you remember that. And the very nice thing about this is that we can train them in a self-supervised way, therefore enabling them to train on such large data sets. So we can just use all the web data or so and train it on all that data. As the title of the lecture, I used a bit more broader term that is called foundation models, coined by Stanford University, where it's defined as any model that is trained on broad data. So just general data, we don't have to manually label that. That's why the default thing is to use it as self-supervised learning. And then we can adapt it to a lot of downstream tasks. So it's a bit like the basic of any AI application. And you're seeing already there's a lot of related terms. So large language models are typically currently the most commonly application of foundation models. But in the general term of foundation models, it doesn't need to be text only. So at least from the name, I mean, now I know people also use language models and they talk about vision or so on. But originally the term, I mean, if you talk about language, it should be text-based. So that's why on foundation models covers it's a bit bigger, and you can have other modalities, and we'll have that today too. And then they are typically trained in a self-supervised way. So you could also call them as self-supervised models. The motivation behind is, of course, once maybe we just want to have a new term. On the other hand, self-supervised is currently just the basic idea of doing. But maybe there will be at some point more or different ways of training them, and then they could still be foundational models. You can also call them, people refer to them sometimes as pre-trained models, so that they're trained for something and then you continue. We'll see today that that was at the beginning the case. The interesting thing is that nowadays, partly you don't need to do the second step. So they are at least, I mean, to be very good, you should do something more, but you get surprisingly strong performance already just after this type of pre-train. Yeah, so what we want to do today is we'll have a look at the LLM basics. So an LLM, like large language models, have a look how they really work. And this is really more a repetition, because all the components, you have learned them all. And we just see how what like of these components, which things put together are referred to as a large language. And then we come at the first very interesting point to or maybe the most interesting today, as new ways of applying them. And that is what is referred to as prompting and as in-context learning, where we have a different way of using examples and learning from examples that we couldn't use before. We look a bit into also the training, especially like, since we have to train large, what are the right trade-offs? So how to do that? And finally, how we can extend that to more than one modality. So currently, at least, maybe it will change, but currently, typically the backbone, so the main component of any foundation model is a large language model. And then we plug in their components which have abilities for doing understanding images, audio, or any other modality. Good. So what is a large language model? It's basically what we had already, and we refer to as a decoder-based model. That is exactly the structure that we have. So we have a unidirectional model, which is trained on the next word prediction. It's like a transformer architecture where we put in sentence start, then generate the first word. We put in the first word and then predict the second word, and so on. And this type of architecture is at least currently the most common one, and in this type of large language models. Although it's not the only one. We had mentioned one problem of decoder-based models. Does anybody remember, or what is maybe a weakness? Yes?
The scaling of the context line.
The
scaling of the hardware requirements in the
yes, I mean, yeah, if you have very long context, that's difficult, and there's a problem with for transformer and so on. Yes, but I only can say it's not what I wanted to point out. Sorry, but it's completely correct. So everything right. Yes.
But only go in one direction.
Yes, exactly. So that is the other idea. And so that's why there are also encoder-decoder-based models. I have to admit, or like, it is good to know. So this is not the common use for large language models, but they are still used. There's things like T5, for example, which is a model which was trained in an encoder-decoder-based architecture. we have there the advantage that the input can be processed in a bidirectional way, while the output, of course, can still only be processed in a unidirectional way. Yes.
But why exactly is it better to have it processed like in both directions?
I mean, the idea is that it might be easier to resolve ambiguities and understand them if you have a look at the whole sentence and not. So otherwise, if an ambiguity, or like if you, in order to resolve an ambiguity at position 2, you would need to have information from position 20. You can only resolve that after 20 steps, and you might have forgotten about it. If you have general access to everything, you can directly resolve them. So that is a bit the motivation, but it's already a good argument for why it might be not so important. There are two things. I mean, on the one hand, of course, this may be an extreme case. Human is also reading from left to right, at least roughly. So we are designing a language in a way that it should be not too complicated. And these are very over-parameterized. Typically, we have a lot of features, so that's why it's possible. This also, of course, has a disadvantage. Typically, training is less efficient and more difficult than this very simple next word prediction, which we have for the autoregressive decoders.
Yes. And also, wouldn't it be the same problem with stuff that is in the middle of the sentence now? If you look at the end and the beginning,
no, but in Transformer, you look at everything at each position at everything, so you can always access everything.
Okay.
Good. So the example is here. I mean, GPT is one of the biggest, the most famous architectures at the moment. You see here how it is. You should roughly like reassemble this. This looks like we had already also in the decoder for the transformer architecture. Although, of course, if it's decoder only, we don't need to do cross-attention layer. So maybe you remember that between the mass self-attention and then afterwards, we have typically this cross-attention, which attends from the decoder to the encoder that we don't have because we don't have one. But then this is the typical thing. I think this is from GPT-2. So we put in the text and positional encoding because it's transformer does ignore the word position, so we have to encode it here. Then we have here the mass self-attention mass because it's decoder only, so we should not look into the future, but only look into the past. Then there is a residual connection around it. Afterwards, we have the layer norm. Then we have the feed-forward network, again with a residual connection, again a layer norm. And then this is repeated for example, 12 times. And then we can do text prediction or text classification or something like that based on that. So this is really like very similar architecture to what we have seen throughout the lecture. And that is the general architecture that we see. You see, it's already a bit larger. So we rarely had like 12 layers here. So it's decently big. But the general idea is very similar. Then we can train this in a self-supervised way. So we just do this next word prediction where the advantage is we get feedback at every position. So we get a lot of feedback. When we have one sentence at every position, we are learning what is the most probable next word. But of course, yeah, we have no separation and it's unidirectional as before. But I mean, the training is also what we had the whole lecture about self-supervised learning. So it's somehow maybe the most commonly used self-supervised learning method at the moment. And that is exactly trying to do that. And that's then roughly the type of architecture that we have. And here a bit of the sizes. So there's different versions of all our architectures. I've shown here a bit that you get a bit of a feeling of that. For once, here is GPT-2, and then we have GPT-3 on the next slide. So here we have 4 sizes. The smallest one is the one with 12 layers, and then a hidden size of 786, which is like then similar to GPT-1. Then if you have BERT, does anybody remember BERT? So it was also a transformer-based model, but it was bidirectional. So it's more like an encoder. It's, I guess, the most commonly used encoder, pre-trained encoder that's out there. So that would be the size. So 300 million parameters. And then here are versions of 700 and 1.5 billion parameters. Just by increasing both, you see people increase both. On the one hand, the number of layers, and then on the other hand, your model size. Then the next big step was GPT-3. And there you see that things even got bigger. So the smallest here started with 125 million. And then it goes up to 1,000 times as big. So 175 billion parameters here. That is like the biggest one, or what is typically referred to as GPT-3. Only, yeah, afterwards people stopped publishing how big GPT models are. So it's getting a bit more problematic, but you see here a bit what that is. So you have then nearly 100 layers. So this is the dimension to the top. The width is you have now hidden sizes of 12,000 entries, and these 12,000 sizes are hidden sizes split up into 96 heads, so that in each head you then have a dimension of 128. So you see already, if you look now, GPT-2, GPT-3, that was like a quite big step. Performance really improved. But the main difference is here not that there is a new great architecture or so, but one important thing is it just got bigger. And that's, of course, on the other hand, a very nice sign. So it's really machine learning. So we have the basic component, and now it's only about like making the model bigger, training it on more data, so that you get stronger and stronger performance. And this is now like our language model. So the question is, how can we use this as a useful tool? Based on what we until now did, what would be one way of how you could use such a pre-trained model? This would be your task. Any idea? You got this great GPT model, and you have all your knowledge you covered until now in the lecture, and you got a task to do something with it, to solve some helpful tools. How would you process, or how would you continue? Yes?
I mean, probably quantize the model and then fine-tune it to the task we need to do.
Yes, exactly. So the quantize is even, yeah, more details than yeah, it's right. So we need to do that. The important thing is we would do some type of fine-tuning. So you would have hopefully some task data, or if not, you would ask, if it's your job, you would ask your boss or customer, I need some data to fine-tune on. Then you take this task and you would fine-tune the model. Typically, fine-tuning means you have your model, and then you would train some type of classification head on the top, either to summarize everything if it's a class, or like at every word some classification, so that you could do some type. So this is what is the default way of transfer learning, what we had. So we learn general knowledge into the model, and then we take this and then learn the specific things by training dedicated layers, for example, on top of that. Okay, so did we really? I mean, this is nothing really new. This is all what you have. So what is the big interesting thing about large language models? And that's what we want to cover now next, and that is about application. So we had now one way of applying it, and that is by like fine-tuning on a task. However, the very interesting thing is that language models or large language models, if they're large enough, they're even more powerful, and we can do tasks where we even don't have the additional training data. And they work surprisingly good at that. So that's what we want to do somehow now in the next steps. So how's that? The basic idea here is what is referred to as zero-shot ability. So zero-shot means normally you need examples, as we have seen in fine-tuning, you need data, and then based on this data, you can learn task-specific knowledge. You can learn how to classify things into cats and dogs or something like that. The question is, can we also do things without any examples, so that we can't do any updates? I mean, until now, when we want to do learning, we would update our parameters, learn new ones, like the one in the classification had. But is that really necessary? Or does the language model have already, have all the information so that we don't really need to do any additional training? And that's why, therefore, it's referred to as zero shot. Well, later in context learning, it's going into one shot and few shot. So one shot means, okay, you need one example to demonstrate what the task is, and then you can solve it. Or a few shot, not surprisingly, you need like some examples to do that, and then it's possible to do this task. So how can we do that? We can only rely on the ability of the model to predict the next token. However, a lot of tasks that we want to do, we can describe in a way that it's in the end a completion task. So, for example, if you want to know, like you want to do named entity recognition, I hope you can remember, it's just like extract the names from, or like, or determine where like what are the names mentioned in a sentence. So yeah, if you have this sentence, I fly to New York, and I mean, for you, it's easy to see that New York is a city. But if you want to do that with a computational approach, of course, it might not be super easy, because if it's like to my new house, then it's not a city, then it's just like a thing. So you want to do somehow, you want to classify what part of the sentence is a city. What you can now do is you try to transfer that into a sentence completion task. So you can generate a sequence, the sentence, I fly to New York, mention this city. And if you think now about that, what should a language model do? It should like do the most promising or the most common occurring completion of the task. What is the most common completion of this task? Yeah?
I fly to New York City.
Hopefully only New York or New York City, because I mean, you ask the sentence, I fly to New York, mentioned the city, and then you hopefully will say, okay, the city that is mentioned is New York. So it should put New York. So if you give this prompt to the language model, so you tell the language model, continue generating when this is the start of your sequence, then hopefully it will learn that based on all the knowledge that I gather in the text, the most meaningful completion of that would be New York. So you have solved your task. So if your task was to identify cities in the sentence, then you no longer need to build a classifier on that. So what you just do is you phrase your task as a sentence completion task. So you transform your task into a completion task, and then it can do exactly what you want to do. So you don't need to train a classification head. Remember, we had this named entity recognition where we would have, like as we are seeing before, we would have a head on each of the hidden states, and then we do classification city or non-city and so on. What we are trying to do with language models, since they are good in generating fluent text, we're trying to make this into a sentence completion task. And by this way, we can do that. So we don't need to train any additional classifier anymore, but we're implicitly doing that, but just doing the completion of the full sentence. There is another way of doing that. The other thing is you can do if you have only a fixed set of properties, you can do a discriminative approach. So a large language model not only can generate text, but it can also give you the probability of a text. So if you just multiply all the output probabilities, you have a general probability of the full sentence. And then the idea is, if it's a correct sentence or meaningful, of course, a language model should give a higher probability than a sentence which doesn't make sense, because it hopefully has seen more sentences that do make sense and that fit than other ones. So that is more common to the training data. So you could have something like, if you want to determine whether it's like now it's a sentence, a spoken language understanding, so slot filling, you want to know whether New York is now the arrival or the departure city, So you can, I fly to New York means that I depart from New York, or I fly to New York means that I arrive in New York. You can give the both sentences to the language model and calculate the probability of these both sentences. And again, the model will like look how probable is. And for the second one, now for the first one, it should not really fit. It should learn that their depart has a relatively low probability because it's like somehow contradicting what you said before. Therefore, the probability of the first part should be lower, and that you can then use as a classification task. So you have solved the classification task by just comparing two string probabilities of a language. So, and that is a big difference now and it makes it possible to do zero-shot classification, because we don't need to train any specific classifier anymore. We are trying to phrase everything as a sentence completion task or as a sentence probability task, and can do it by this way. And exactly this way of generating the text, that is what people refer to as prompting. So it's about encouraging a pre-trained model to make a particular prediction. So you give it some type of prompt, and that is the only thing we have to do. You have to phrase your task as a prompt. So you somehow have to phrase your thing as a natural language thing. Of course, this is on the one hand really, really great, because this is something where you don't need that much deep learning experience. You don't need programming skills. It's a very natural way, so you just need to speak the language. And there you can do a lot more. So for example, here is an example from, you can do it into question answering. So when you want to know who has developed JDK, you make this as a sentence completion task. So JDK is developed by, and then hopefully the most probable answer to that will be Oracle, because that is as seen somewhere in the training data. So of course it only works. I mean, the large language model is like trained to predict most probable next word. So what it mainly does is it stores somehow all the information from the data. On the one end, of course, on the syntactic level, so how sentences are constructed, but of course also on the semantic level, because most data should somehow semantically be correct. We write often about planes that fly, but you rarely write about planes that are swimming. So it should learn that, yeah, planes typically are flying, or like birds can. And then it's just like you more often will find that and have learned that the most probable completion is flying, and it shouldn't be a thing. Very interesting or very nice. I always see this example. So I think I mentioned in some other lecture already. So I guess you might have heard about this TLDR. So somewhere in emails at the end, there is this TLDR, too long, didn't read. And then people put a very like one sentence summary of what was written all before. A good language model, which has been trained on a lot of text, should learn that after TLDR, there is this brief summary of what has been all said before. So we can now encourage the model to do exactly the same thing. So if you want to summarize, we put the very long text and then we put a TLDR afterwards, and then ask, okay, what is now the best way to continue doing that, to summarize, to complete this sequence, and that will be a summary of all that. Of course, you have to be trained on really, really much data, because otherwise it might be hard to learn this correlation. It's quite difficult correlation, and it might first initially just put some random things which are always in a summary. So in summary, we did X, Y, that, and we'll always say in summary, we do X, Y, that. And it's not connected to what was said before. That, of course, is an issue. We'll talk about that, about confidence, about hallucination. So that's a major issue of large language model. But the general idea is really that we're trying to transform any type of task that we're interested in a task that we want to complete, like in a sequence completion task, so that it's like in a very natural way. Maybe how you would phrase it for anybody else, or a human to write it at the end. Yes, any questions about this?
That's part of the multimodal architectures chapter, right?
No, this is on the Good point. This is all about the first one, the application. Oh, this is about prompting multi-model. We'll come later to the multimodal architecture. Yes.
Regarding the multimodal,
Yeah.
One time I tried to say, please draw as an ASCII art I don't know which creature it is. I think it was a unicorn or something,
Yeah.
and it's drew a ASCII art. I would like to know. It's also an completion task,
Yes.
but I don't know how, because in the text there is no description or on how unicorns look like. So how does it from just the text get how it would look like as an ASCII art?
I guess it has seen a lot of unicorns in ASCII art. That is the thing. I mean, if you Google for unicorns in ASCII art, I guess you'll see a lot of ASCII art unicorns in the internet.
I mean, I just said unicorn, maybe it is,
but I think it will. I mean, I'm not, but I would assume it will mainly work for things where you find things in the internet. Yeah, if you draw the campus of KIT in ASCII art, I would at least be skeptical that it works. I haven't tried it, so it's always a bold claim that it doesn't work because sometimes they're surprisingly good. But I mean, it's mainly recalling that unicorns look like that in the internet or in the training data. So it has seen that. So in that way, it's also a completion test. And I mean, that is of course a bit of a problem that people claim it doesn't have a really understanding of it, which partly is true, but I mean, then of course it gets interesting how far it can generalize. So, maybe if it has seen a lot of animals, it sees also patterns, how ASCII arts draw animals, and maybe then it can even do another one. I'm not sure. So there will be some border where it doesn't work anymore. But that is exactly there. It's still again that it tries to like, what is the most probable sequence of generating? Yeah, here you see that this really got a lot of attention. So it mainly was introduced in GPT-3 a bit before, but you see then here's the number of publications. It's really like then within 2021, it got a lot of like interest in that. And people are doing that more and more, both on research side, but of course also there's a whole like business case now as what people refer to as prompt engineering. So where it's like the job is to write the right or come up with the right ideas, how to tell the models how to complete. Of course, prompt engineering is maybe from machine learning point of view, not what we want to have at the end, because they should understand anything. And what you try with prompt engineering is a bit like, okay, how do you have to modify your input so it does what I want? We want, of course, at some point to get somewhere where it's no longer necessary, but yeah, currently that's still often the case. So what is a big difference? So there is a really big difference between prompting and fine-tuning. That is somehow the two things that we have seen for now if we want to adapt the model. If we're doing it prompting, we describe the task in natural language, and we often even don't have to give an example. So if you want to translate, it might be something, translate English to German, then you give school, and then you ask it to complete the thing. In fine-tuning, we give several examples. So we give one example, then we update our parameters. We give the next example, we update our parameters, and so on. And we do that for several times. And then when it's done, then we can finish this thing there. So yeah, so this is very important to claim. So you don't change your model in prompting. The only thing is you do everything on the input, which of course is also nice. That means you can directly apply them there and so on. So how does prompting in general work? And that we want to do a bit more detail and also look at some examples to get a bit the idea of it more. So in generally, if we have any task, what we typically have, we have our input. If it's about now language modeling, so natural language, it's some type of sequence of words. We can't yet work on multimodal, we'll look into that. So first you have a sequence of words, and what you want to do is that you want to generate some type of output label for that it's generating an output. There can be, for example, things like sequence classification, where there is one label, or a sequence models, where there you want to generate a sequence of words, sequence labeling, where there are several things, and so on. If you want to do that now in a prompting-based way, what you start is again with your example. Then you have to have your prompt addition. So you have to see how you can make of you have to have these rules, how to make out of your example, how to make a prompt. Typically, this is done by a human because, I mean, this is, you don't have to learn something completely. You have to do it once for doing translation, once for doing any task. But of course, there is then, on the one hand, you can try to improve. So how can you do the prompt addition better? So, for example, in translation, people found out that if you just translate from a language A to B, you have a worse performance than if you say, please translate like a professional translator from A to B. Because then you will more find the examples where people mention that this is a professional translator. So there's, of course, both. There can be a lot of work on the human side. There's also, we'll cover that not too detail here, there's work on research and automatically learning the right prompts and changing the prompts and paraphrasing things. You can, again, then somehow backpropagate through and think which prompts are more helpful. Of course, it's getting complicated because prompts are discrete, and like changing discrete things is often a bit more complicated. But of course, there is ways of doing it. Then you end up with a prompt which consists on the general description of the task and your example. And then you would do the answer prediction. Who would do the answer prediction? Which model? Yes?
Just the LLM.
Yes, so this is what just the LLM does. So it gets a prompt and you just let it do the prediction to continue. So this is the work of the LLM. You might have to do some type of mapping at the end. So we saw that in the one example. At the beginning here, for example, you would have to map which one means departure city and which one means arrival city and so on. But that's typically very, very straightforward. So the most interesting thing we'll look into a bit is the prompt addition. So how can you do that? Typically, they have this type of phrases where you have on the one hand the input and the template, and on the other hand the label that you try to predict. So if you want to do something like sentiment classification, meaning you have, for example, you want to know what people think about like if you have a description of a movie, you want to know, is it a positive rating or a negative? So it's a two-class classification problem. You get a movie rating, like on Netflix or so on, people give comments, and you want to know how to automatically classify, is this a positive rating or a negative rating? Then you can take something like this template, so X for your input, and then you follow this up. Overall, it was a Z movie. So something like if you have then the input, I love the movie, then you have the prompt, I love this movie. Overall, it was a movie. And then you ask the model what to put there. So we'll see this is not a completion test, and then you would have to remove that, but you have also sometimes this infixed ones. So, and then you can either test a fixed set of 3 possible, it was a good, bad, or excellent movie, and then you can check which one got a higher probability, and then you have your labeling done. So you can easily, you see here, classification tests, you can reformulate in this type of phrasing. Also, like named entity recognition, we had that bit. So you have in this type, for example, 2 inputs. You have the sentence, Mike went to Paris, and you have a candidate Paris, and you want to know now if is Paris a city, is it a country, or is it a building or anything like that. Then you can do the prompt like this. Mike went to Paris. Paris is that entity. And then hopefully it will put their city entity. I agree with, I guess you will say this doesn't sound like a natural sentence. Yeah, so partly this of course gets constructed. But again, you see, you don't have to train a dedicated classifier. all you're doing is doing like either inserting words at the beginning or like inserting words, in the middle or at some point in between, and thereby hopefully you can solve this test. Summarization, we had that with TLRDR. So you have natural processing as a field of blah, 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 and then you put TLDR and then let it just continue things. So again, you can do also sequence generation tasks. You just have to once learn what is a good template. Sometimes you have to also play around with it a bit. A lot of work nowadays in language models is trying to really understand, or not, but like getting, analyzing the behavior to find the right ways of that they behave as they should be. Or translation, something like I go home, then you can, for example, one typically template is like English, you put your input and then you put German afterwards, and then. So what you always have as an aim is your template should look more similar to your training data in a way. So if you know that translations are typically happening this way, then this is good. Because remember, it tries to do the most probable sequence. And if this type of pattern happens a lot of times, it's very easy to complete it as it should be. So you have to, in prompting, you have to find these type of templates which are typical in your training data. Of course, it's difficult because you don't know the training data, but then it's more about generally, how is it? I mean, you know that it's mainly trained on large parts of the internet. So what is a common way of phrasing it in the internet? Because then you'll find it and it will behave a bit more like expected. So you saw already there's two basic ways of prompting. There is a prefix prompt where it's about continuing things, and there's a close prompt where it is somewhere in between. If you have now a language model, of course, it's in between. What you mainly can do is some type of like score then fixed number of candidates here, while here you can do really the open ending thing at the end. Or you have to do here some type of decoding where you force the model at the end to also generate the movie and then hopefully find the most probable one. Because why maybe you want to have movie in here, because maybe that forces the model that, yeah, while doing here, it will change which one was probable before, because you have this ambiguity. So sometimes it's preferable to have some like close prompt at the end. And yeah, that is then the total thing of the prompting. So it's really these three main steps. And in a way, therefore, it's a lot easier than training a dedicated classifier. In just prompting, you don't need any examples. The only thing you need is a natural language description of your task in order to do your task. Good. Any more questions to prompting this way, or everything clear? Good. Then we come to a related topic, and that is what is referred to as in-context learning. Of course, it's a bit argued whether this is really learning or not, but the most important thing is this is a term that is now commonly used, so we use it in that. And the idea here is very similar to what we had before, but normally you get more what you really want if you tell, like if you have some examples before, then also the model, it's easier to, like if you think about it, if you again have this prompting view, it's about like predicting the next word. If you have seen some examples how in similar cases the next words look like, then it might be easier to do it exactly the same way. And that is again done in context learning. So we are going from zero-shot learning now to one or few-shot learning. And the idea is that in your prompt, so the same prompt, you're not only describing the task now, but you give 1, 2, or X examples of how the task can be solved. And then, of course, it's easier to do the same type of completion. So if you have the input, add 2 numbers, 6 and 8, then you would give that one example is that 1 plus 1 is 2, that 2 plus 5 is not 9, that is wrong. 2 point, And it's even not my graphics, but it's copied. Okay. And then you would do 6 plus 8, and then you would ask to continue it. In this case, hopefully it will not work because you get confused about how it works. But if this would now be the correct one, you can see then that this would generate then the correct. And it hopefully has more often see what is meant with plus.
This is the two-shot learning?
There would be, for example, two-shot learning, yes. So yeah, we'll have some graphics about that, I guess. But yeah, I mean, this type of in-context learning is very efficient if you have 1, 2, maybe 5 examples. But then at some points, typically you have some diminishing return. And it's also that, of course, it's getting longer and longer. And I mean, one important thing is that the longer your prompt is, the longer your processing is. You have to like process them all the time. That's why you always want to have not too long prompts at the beginning, and including the in-context learning examples. And yeah, there's rarely like that you have like in normal machine learning 1,000 examples or something like that.
And how long can the example be? Because you can condense both examples in one, and you say this is a one-shot.
Yeah, I mean, normally, one example is like how long also your input is. So it's like input output pair is one example in this one. So you would treat this as 2 examples in that. Another example here, for example, for translate could be that you translate English to German, you get house, car, auto, school, and then you ask the models to complete. Then it has understand, or like it sees that this way of having like there are arrows in there is like showing that it should be the translation, and then hopefully it will work better in a way. So you typically see then that the performance, especially with 1, 2, or 3 examples, really improves because you make clear what you're really expecting. So you give some examples. I mean, it's like for you too, when you get a new task, often it's easy if you have seen 1 or 2 examples, it's easier to solve the task because you know the format and you know have the general idea. While if you get a task without seeing any example of that, that's more difficult also. Then, of course, by having that, comes additional challenges. So one question is, what examples do you want to take? So, of course, if you only have 2 examples, then you take all and that's it. But in a lot of cases, you might have more than 2 examples, and then you don't want to put all the examples in there. So the question is, which examples? Do you want to find more similar examples? There's been research that you're not randomly, or you can take random examples, or you can do some more similar examples. I mean, with numbers, it's maybe a bit boring. It's like, yeah, you take maybe where the numbers are similar, but maybe if you have now natural language, if you have translation, you can look at sentences which have similar meaning or similar lengths, so that you have similar sentences. Or maybe you want to have dissimilar. If you think about labels, a classification task, it might be good that you have, for example, 1 positive and 1 negative example. If you only give negative example, the model will learn that, oh, you just always have to say no, and will always say no. So it might be good to have examples for the different labels that you have. And even the sample order can be of quite an importance. Maybe that's sad, but again, they're not perfect. So people have found out, if you look at the prompt, I mean, you have to see that as a long sequence. And now what we're doing, again, get back to the architecture, what we're doing is, when we are now generating the answer, that's our self-attention. So we are generating the next token, and we're always attending. And then, of course, it can attend to all the words before, but I mean, for example, in natural language, it's trained on language, and there we have learned that the previous ones are maybe most important. So it might attend to the last ones more than to the initial examples. Also, it might be typically at the beginning of an article, there's the most important information in order to understand later stuff. So the beginning is important. So what you often see is the U shape, where most attention is paid to the beginning of your prompt and to the end, because that is what's near. And that, of course, you have to take aware in a way that this might be important in order to order your examples. Also, to where describe the task. So often you have both like a combination of some examples and a description. Or if you think about question answering, then you have like, you give a text and you ask a question to that and you want to have the answer. Then it's of course a question. Should you first put the question, then the text, or first the text and then the question, and so on. Good. So how good does that work? And this is maybe the very interesting thing. It really works quite well. So superglue here is some language understanding test. There's a set of like 100 tasks or so where they have to do an identity recognition. A lot of tasks about understanding natural language. What you see here is like 4 baselines somehow. This is a classification test, so you can do random guessing, and then you're somewhere between 40 and 50%. You can do fine-tune different BERT models, so it's all either language classification or sequence labeling, then you get something around 70%. If you have the best model, which has a lot of combinations, you nearly get to 90%, which is also the performance of humans. The interesting thing is now here, this is few-shot learning with GPT-3. So the baseline, if you just do it 0, just by a description, you are already above 50%. So without having ever seen these examples, is already there. Then you're getting to the area of where fine-tuned models are here with 1, 2, 3, or 4 examples. So that's very, very few. Typically, we'll need hundreds of examples to learn. I mean, you cannot do a gradient descent we had before with 4 examples. You'll heavily overfit. I mean, we always had larger batch sizes and so on. So it's really hard to fine-tune a large models with 4 examples. And here you see the largest model has the largest number of examples here is 32 examples. That's nothing for doing some type of machine learning. So you see that you very fast can like adapt to the task and be better than standard other methods. Of course, typically, if you really train a very dedicated model, put all your effort in here and have 5 PhD students working on that, you can get better, you can get really good. But what language models are really interested for is for all the tasks where you can't spend super much time, but you want to have a decent solutions very fast. And you'll see that a lot of people will say, oh, GPT doesn't work on that, or large language model don't work for that. And there is an expert who can do a better solution. That's very often the case. But one interesting thing is that with very few examples, they have a good performance. And for a lot of things, a good solution is decently enough, and you might not need to have the very, very best solution ever. What is another important point, and here is really this typically this learning from examples and also the 0-shot mainly works when you have enough data. So you have to train big enough models. There might be the disadvantage, that's why we put a bit more effort on training, is that you really need to train a lot of models to get that good. So what we have here is, so you have a 1.3 billion parameter model, a 13 billion parameter model, and the 170 billion parameter model. Then here's the accuracy again on some data sets, and the number of examples here in context learning, 1, 10, and so on. And what you see is the small models, they get better with small examples, but only a bit. There's always 2 lines. You have the dotted line, which just gives the examples as tuples, so maybe but not a natural language description. And you have the straight lines where there is also a natural language prompt describing that. You see, especially for the strong models and with very few examples, you just a lot faster can learn. I mean, of course, without a prompt, it doesn't work at 0 examples, because if you just give the input, the model doesn't know what to do. I mean, there you can't do. But once it has 1 example, seeing, then it somehow might work even. But it really needs some examples to learn what pattern you want to have. So if you think about the machine translation task, you would put source sentence, target sentence. I mean, it doesn't know that it should translate. But if you put source sentence, target sentence, another source sentence, then it might already learn the pattern that, oh, this is, you always have the translation afterward. And if you do that 10 times, then you're already very good. and you might not really need the natural language description anymore, that this is a translation task. The model can infer that automatically just from the example. But for very few examples, you see that you really get a lot better. And then you really have already a decent, good performance for large models with 1 or 2 examples. But you again see here how important it is to be really, really on very large models. Yeah, one last extension to this prompting and in-context learning is then what people refer to as chain of thought prompting. So the idea here is that sometimes it's better not to ask the model to do like one single, but to have more computational power so that it hopefully prevents doing some stupid errors. So the standard would be, so you have here one in-context example. So Roger has 5 tennis balls. He buys 2 more cans of tennis balls. Each can has 3 tennis balls. How many tennis balls does he have now? And then the answer is 11. Hopefully this time it's correct. And then here it's a cafeteria has 23 apples. If they use 20 to make lunch and bought 6 more, how many apples do they have? And they tested it on one language model. And you see, especially numbers are typically difficult for, or calculation for language models, because it's not what they're really made for. They're mainly trained on text. And then it's giving here the wrong answer. The wrong answer is 27 here. So one way of trying to do that is trying to get the model to that it not just like gives the answer, but it uses more computation to calculate the answer. So you're given an example, a way of how it can be derived. So again, we have the same question, but now the answer here that you tell it should give is not, the answer is 11, but Roger started with 5 balls, 2 cans of 3 tennis balls, each is 6 tennis balls. 5 plus 6 is 11. The answer is 11. So you have to give the full explanation as you might have to do in school. And so then the model will try to repeat that. And then it's down here. The cafeteria had 23 apples originally. They used 20 to make lunch. So they had 3. They bought 6 more apples. So they had 9. The answer is 9. And you really see that the models are like, there is several research as well. Several tasks, it's helpful to do something like this chain of thought prompting so that it not directly gives the answer, but it has to explain the answer. It uses more computation, of course, there, but also has to do smaller steps in order to generate the correct answer. Any more questions to that? Good. Of course, there is several weaknesses which are getting more and more addressed. I mean, in some way, especially if you have very long prompts, things might be very inefficient. So if you have a very long description, you always have to run this. So if you already see this example, in order to solve this task, you always have to first process all this, and then you can do the prediction. So things might be a bit efficient. Yeah, it's performing less good than fine-tuned, but as I said, often, I mean, this is only partly true. Models get bigger and more strong and so on. But of course, yeah, I mean, that's the thing with multitasking. Often, if you have a model which can solve a lot of tasks, on an individual task, it might not be as good as like one model, which is only dedicated to this one task. On the other hand, you have more flexibility to that. It's still often sensitive to the wording of the prompt and the example that I have given. And yeah, I mean, the clarity, of course, hallucination is an issue. And that's where we have next week an extra lecture. Yeah, this prompt engineering is the idea of creating this one. The advantage is you have seen now you can very easily develop solutions to do something, to solve math tasks and so on. So you don't have to train a large model. You have to give 1 or 2 examples and so on. You can do that in natural language description. Of course, the problem is we are not really always knowing if we change the prompt, what do we really change? And that, of course, comes also with a bit of a danger because you don't know for what people in the system will use. And maybe then it will behave very unexpected in a way. And it's important to know that prompts, of course, are somehow depending on the model. If one prompt works well for one model, maybe the other model was trained in a bit different way and so on, and then it might not work anymore that well on that. Good. Any more questions to prompting on this? Then next we want to see some examples from 2 papers about how to select your sizes, because we already hopefully have motivated here that size is really an important thing. So there is now several decisions you do in size, and therefore it might make sense to look at it. So first of all, this is here not a performance like a scoring, but it's like a test loss. So you give some training data and you can calculate how probable the training, give some test data, sorry, and then you can calculate how probable this test data is. Since you know it's correct text, you want to have a good model to give a high probability to that. Or like a small loss, which is like mainly based on the negative of the probability. And what people have investigated here is, on the one hand, you can look at how many computations you have done, so how long you've trained that. And you first see that always here, the longer you train the model, or like the bigger, I mean, it's not only longer, it's more data and more parameters. Because computation is both. If you have a bigger model, you need more time for the same type of data. So in order to improve your, or not improve, to make it worse, so to need more computation, you either have a bigger model or you have a bigger data set. And here they have built a lot of models with different sizes, and you nicely see that the performance, the best performance here in black for each of the computation, like, is following a power law. That means, it's going down, but you see here it's like exponential, while here it's linear. So if you double your computation, it's not that you double your performance. It's like if you quadruple your computation, you double your performance. So it's more on a power level thing. And the same thing is if you look at data sets and parameters. Of course, it's not completely free. So here you again see you increase your data size and keep the parameters the same. And you nicely see the more data it sees, the better it gets. And you increase your parameters, and also it's going. Of course, it's not completely independent. If you have a very small model, more and more data will not help you anymore. And if you have a very small model, so very few data, it's also the large models at some point will not help you. So they have to somehow fit together. But that is one important question we want to address here. If we have unlimited data and can have unlimited large models, what is a good weighting? So should we increase our model size, or should we increase the data that we are processing? Because, of course, this computation is really expensive. So here is the training time need for different models. So BERT and Robera, T5, I mentioned the encoder decoder based models, and here GPT-3. So small to the really big size. And you see, of course, the bigger the models is, the number of training petaflops, so the number of calculations you have to do is significantly increasing. And this really gets more expensive. So people estimated that in order to train the largest GPT-3 model, this costs you like $4.5 million. So it might not be something that you can do, that we can't do it anyway, but even as a big company, you might want to consider this and think about what is like how can I build the best? You cannot run like 20 tests and try them and then take the best one. So that's why they have to consider what is the good ways, and you cannot do hyperparameter search or something like that in this site. And it's not only about money, there's also other things. So here's, for example, the carbon footprint, so how much CO2, so how much energy you use. And of course, also you see the training this type of models is really expensive. So you should consider, well, and you can't do like just pure gradient search. So you see it's like a lot more than like we spend in a year of our life. Yeah, I guess that is human over the world, while this is like an American. I guess it's even not over all humans. I guess that would be even less, but yeah, I'm not exactly sure. But you see that, yeah, this type of training such a big model really needs a lot of energy, and therefore you should consider. So how can you, if you now see it from the other way of view, you have a fixed amount of energy or CO2 or computation for simplifications. If you have a fixed amount, what should you do? Should you like how big your model should be and how much data you want to look? And there has been some research on that and investigating if we want to build a large model, what is the best performance for a given budget? If you get $1 million and should now train a large language model, then you have to do a bit of a decision. So how big should the model be and how should I train it? And let's assume for simplicity, our budget is given in floating point operations. So how many calculations we can do. And the parameters which we're interested in, of course, it's a bit an approximation, but it's on the one hand, the number of model parameters, and the other thing is the amount of training data. That is, yeah, somehow. I mean, the good news is that, for example, it's less, if you do decent decisions, it's not super sensitive to like how you distribute your parameters. So if you do double as many layers or double as wide layers and half the number of layers, the performance difference is not really super. It really heavily just depends on the number of parameters. Of course, always in some reasonable boundaries. And there is this estimation that the number of calculations is at least proportional to 6 times the number of parameters times the number of training data. How do we come to this type of calculation? So what is the most calculation cost? Are matrix multiplication that we're seeing. So you have to do this type of matrix multiplication. And which multiplications you have to do is mainly you always do this multiplication of the hidden state times your parameters. So this is like the most of the parameters is somehow you take your hidden state and multiply it with your weight matrix. So roughly the number of operations is like the number of matrix operations is n. And then it's like in a matrix, you multiply the two values, you add up. So it's 2 times n. So a forward pass with one data point, a very rough estimation is something like around, it's proportional to 2n number of parameters. If you now do that for each data point, it's 2n times d. So the forward pass is 2n times d number of parameters. For the backward, they also do a very rough estimation. So you have to do the backward pass, and the backward pass, you always have to calculate the derivative on the one end to the hidden state, and on the other hand to calculate then the gradients, and you have to backpropagate for the hidden state, sorry, for the hidden state in order to backpropagate further. So in order to get the gradients in the first state, you first have to backpropagate from the last to the second last and so on. So you have to, for each hidden state, do this multiplication. And for each parameter, you also have to calculate the derivative. So it's estimated as 4, and in this papers, they often assume something like 6nd times is the number of calculations that you have to do. So how do we select these n times d? And there's 2 versions of the scaling law, where the initial claim was by Kaplan et al. In 2020 from OpenAI. It depends a bit also if you have a fixed batch size or if you do like an optimal batch size, depending on both. And it's a bit like if you increase d by 1.5, so sure, d was your dimension. D was the amount of training data, sorry. If you increase by 1.5, then you can increase the number of examples, your data, by 2. So the D was the amount of training data. So that can be improved less than the number of parameters. So you can faster improve your parameters than you can improve your training parameter. And it was a max, if you do optimal, and that was cited a lot of times, it's even 1.3 to 2. So you can really more strongly improve your parameters. And then there was more work by DeepMind, the so-called chinchilla law, we'll see. And there they did two different types of experiments. First, they fixed n, and then they used 3 different d's. And then you get these curves here for different values here of your parameter size. And then you have here totally the flops and the training time. And you see that here's always the best performance. And then they can check for each C, so for each flop here, maybe here it's a blue one, and here it's a red one, and so on. And then you can check what is always the lowest performance. They do a second type of experiment, the so-called isoflop, where they fix C, and then they choose different n's, and then we have the formula. So based on n, you can then apply your D and do again more examples. You see, this is quite computationally expensive, and typically things only is done by big companies. And then they came here to the different way, where you have these coefficients, how strong they increase, and why by Kepler it was mainly based on the parameters. Here you see that the increase should be similar. So this type of coefficients, how strong they are correlated, the N and D based on C is like roughly half and half. So you should improve also your data size fast enough. Otherwise, it really doesn't help you with huge models. If you don't increase your data size fast enough, you cannot train efficiently very large models. And this led to the chinchilla model, and there you see they exactly did that. So you have here of some different models, the number of parameters and the estimated number of tokens they are trained on. So based on the chinchilla model, they only took a 7 billion model, I mean, compared to that, but it was trained on 1.4 trillion models. And they could show that, I mean, this one, too, I think, have a similar computational budget, but they got a significantly better performance with this. So you see there is a trade-off, and you have to think. And currently people try to get more and more data to train them. There's a recent model like half a year ago or less by Llama 3 by Meta, which was really trained again on, I think, 11 trillion tokens by now or so. So people look into how to get more and more and more data, because, yeah, currently at least it seems that it's really important to train on much data in order to get a good performance. Of course, there is another big advantage. If you compare, why would you prefer chinchilla over Hoover? Yes?
It is less expensive inference.
Yes, exactly. So that's the other point. The nice thing is that you increase your training data, but don't increase your parameters, it doesn't matter at inference anymore. So at inference, the lower one is also a lot cheaper. So it's even good if you can get the same performance with a smaller model, but just training on more data, then at least in inference, and if you remember, I mean, it's very expensive to train the models, but now if you think how many people use OpenAI or other of these models, at some point it will be also used a lot of time and be therefore very, very important to be, having a low performance there. Any more questions to? Yes.
What were again, like these empiric formulas to show them?
Yeah, I mean, what they did here is they looked, I mean, here it's very easy. You take for a fixed, and then you just estimate which N and D was the best one for this C, and then you try to generate this type of correlation. How is the N or the optimal N correlated to C to the power of what? And the A here was like around 0.5 value.
So N, what was N?
And C is a complete computation. N was a number, the model parameters, and D is the training data.
Ah, okay.
Okay, and then for the last 15 minutes, we want to now extend this a bit because we call it foundation models, and until now we only talked about language. So how can we now make this into foundation models and using more than one than just language? And this is, of course, especially interesting by now, and you'll see have all, I guess, seen GPT-OV and other multimodal models where you can now both understand image and generate image. We'll today focus mainly first on the case about having images or audio or other modalities at the input. So how can we do that? So in most cases, this is still the backbone. So the main thing of your model is still a language model. And because we have to edit it a bit, so have a look at a bit what is the language model. So the input here is our words. Of course, we are not, I mean, the prompt is fully put it in, the other is generated autoregressive, but from the model, what you have is here, you have integer vector between of size vector, like vocabulary size times the number of the sequence length, where this is a one hot encoding saying this is each word. That's what we had at the beginning. So here at each position, you have this one hot encoding where you have at each index a 1 saying this is the word and everything is 0. And then you have it. So you have in total this vector. To be honest, it's not n, but only 1 and zeros. But okay. And then it's v times n, where v is the vocabulary. Then the first thing is your embedding layer, which transforms this into a dense vector, so real values, where again now we have a hidden size, so that is our hidden size we're dealing with, and then again the same length, so the length of our vector. Then we have here, can have as a language model, typically we have different transformer layers. We learn transformer layers, they don't change anything about the structure. So the input is r to the power of hxn, h times n, and the output is also h times n. So they just do transformations and so on. And then we can have the classification layer, which is here a word prediction layer. And that is then doing this one, the output layer to the vocabulary size, so that you have probabilities of all that. So this is a normal layout of the language model that we have discussed today in all the times, again, more in a mathematical formulation. So how can we now add some type of multimodal content? The next component that we typically have is multimodal encoders. That can be image encoders and or they can be audio encoders. And what they mainly do is they take our input and encode it again into a sequence of vectors. I mean, if it's an image, it might be not really a sequence, but like more a 2D thing of vectors. But you can sequence, I mean, you can also interpret that as sequence. We had that, maybe you remember in visual transformer, that it was also like that you just like linearize your image. So in the end, you can interpret all these outputs typically as something like the hidden size times the number of examples. Of course, here the m, not the n. If you have example, it depends a bit. In images, for example, that is typically fixed size. So you're not having different images having different hidden size, but here it's always the same m. So you do rescaling. In audio, it depends. Sometimes it's also fixed size. Sometimes it's also depending on the length. And of course, that might make a difference. So do you have here a variable size output? So this is always h. Let's assume the hidden size. I mean, we just assume it's the same h. Of course, it could be a different one, but you just put a linear layer to change that. But the question is the length here, is it always the same for all images, or is it different? That is a design decision. And if you have that, then the question is how you integrate these into the language model. So what does it mean? What we need to do is we somehow need to put this hidden representation into our language model and make it also understandable. So you have to connect these two together, because then you can put not only text into there, but also images. and hopefully mix them so that you can also ask questions to the images and stuff like that. That's what we want to do. It should understand all that in total. And there's mainly two main ways of doing that. The one thing is you try to replace some of the word embeddings by your encoder input. So what you take is here is your encoder output. And we said it's like m times the length, so that the first m tokens here you can replace by your encoder. We'll see, maybe we'll have here some connector in between, but in general the idea is that you just replace typically at the beginning. Of course, you can do it also somewhere else, but let's for simplicity assume at the beginning you not have the word embeddings in there, but you replace the word embeddings by some information. And the language model will hopefully then learn how to deal with this. The other idea is to make it internal, and that means you insert inside your transformer layer, you have the ability to then do cross-attention to the image and access image information and integrate them into your language model. So typically this is done. So you have the language model pre-trained, and now you add the ability. So when should I look at the image and include something into there? And that you can do with cross-attention. How did cross-attention work? So we had that already when you remember in the encoder-decoder model. So that is here the same. So the query is coming from your LLM or the decoder. So the decoder is here your large language model. That does a query. And then the key and the values are from here. In this case, it will be the images. So here you have M patches. You just look which ones are important in order to understand the current situation, and then you include them there. So it's the same type of attention before, but now we use the LLM hidden state as query the encoder here, and get the information in there. So it's really like the same type of cross attention that we had in the encoder-decoder based models. One example is here in one. So here they did that as a cross attention. So you do the cross attention from the language input here to the vision input X. So the key and the values are even the same. You just do cross attention. You do here the residual connection, the feed-forward layer, then you have the self-attention and get, and then you can do several times. You see, typically, for example, the LLM layer are frozen. If you add this to your first train your LLM, the LLM is frozen, and then you just learn how to integrate the images. You see, there is some more gating here, and that's why I put it here. So that's maybe interesting. So they do some additional gating. So since there is the residual connection, you can also just have here a 0, then it just does not include no information. And that you do with the gating, and the gating is here not learned. It's learned, but it's one fixed parameter. So it's not depending on your input. You always have a gating here saying, in this layer, should I include information from the image or not? And then you see that it's initialized at 0. So at the beginning, you have the baseline model. You do the calculation, but since the gate here is 0, it will not influence your language model. It does exactly what it should do. And then you can learn, starting from there, starting from a good thing, you can learn whether it's helpful to include this information by changing this gating and allowing to let information pass into there. Any more questions to, yes?
How do we learn to add the gatings if the initialize is 0, then they also have 0 random patch?
I think if it's tangential Bullock, because the gradient isn't 0 at 0, and then it should go. But a good point. So always, yeah, there's a very good point to think about. For the input, then there is some work on how you align the output of the encoders to the language model. So what you want to have is, I mean, in the language model, it expects there's some type of word embedding. So but now if you just have something learned from an encoder somewhere different, they don't really match. So what you have to learn is somehow, how do you match the encoder output to the word embedding layer that is somehow reasonable. And there you can have additional layers. the so-called connector that can be easy, then it's just a linear layer. So you just take the encoder output, multiply it somewhere, maybe change the format so that you can first learn only this type of layer to project the encoder output into the same semantic space as the word embedding, that the language model can easily understand them and not do something really crazy with it. The other way of doing it is the so-called Q-former, which is another attention mechanism, which might be therefore interesting, but there is one big difference in this case. In the Q-former, our queries are fixed. So it's not that you learn them, but that you have them based on the data, but you learn n queries. So in the end here, you have always n inputs. So the image, for example, will be always represented by n words. That is a parameter that you set. And then you learn these queries, you learn the query values, and then you do the attention to the image and so on. So if you think of it like the language model, so these here, where you put words, there you have no fixed parameters that you learn. Then based on these parameters, you attend to your image, you generate what is important from the image and put them in there, and then you get the hidden state. So that was, for example, oh no, I don't have an example for that. So this is a Q format. So one big difference is normally in attention, the input defines how many hidden states we have, because the input is also the query, and you have one output for each query. In Q-former, the query is a learned embedding, so it cannot be different for different sizes. So you have a fixed number of queries that query the image to get information which are important to understand, that you can learn. And then you have here, now, if you have two queries, you have two hidden states, which are put into your language model, which has hopefully the same semantic space as the word embeddings, and you can integrate them there. Yeah, finally, three examples where this is done. So this is one example called Flamingo, where we have a cross attention. You see that. So you put in, this is a cute dog, this is, and then you try to complete it. Here you can even have several images. So you pre-process and put their image and image in there in the text. Then you put your images in the visual encoder. And then you see in the gating, you can do cross attention to integrate it there in each layer. So in each layer, you have the cross attention. So that's a big difference. Here, the visual informations are put into in each layer, while here they are only put at the beginning in there. Another example is this Frozen, where you exactly do that. You have the visual encoder, which is put here at the beginning for a fixed set of words, and then you do like a small boat on the water. So this would be like just pre-training to aligning. So often you, of course, have to learn them and to align them, to connect them. So these connectors or aligners have to be trained on aligned data. So you can, for example, take image and the description, the caption, and try to align it so that it learns how to deal with the images. As last, also here, Lava, where it's done similar. So you take the image, put it through the visual encoder, then there is another projector, and then here you have the hidden states, and then again they are prepended to the language instructions and can be used in there. So you have the ability to combine both visual and language information into one foundational model. Any more questions for? Good, then what you should remember from today is what are large language models? Very important, all the things about prompting. And we talked again a bit about multimodal input. And hopefully this gave you a first idea of how these large language models works. And what we'll then next time do is a bit, now we saw, maybe you think now everything is solved. The problem is the one that was really doing what you expected is not really always happening. So how can we improve it that it, like if we instructed, if we prompted to do something that is really doing what we instructed to do. Thanks a lot, and then see you on Tuesday.